In first semester calculus, when we first started talking about limits, we saw that they had several useful properties. For example, that the limit of a sum was equal to the sum of the individual limits. Well, it turns out that all of those properties, with a few caveats, apply to limits of sequences as well. I've summarized those properties here. For example, the limit of a sum is equal to the sum of the individual limits. This one says we can take a constant and pull that out in front of the limit. The limit of a product is the product of the limits. The limit of a quotient is the quotient of the limits, but we do have kind of our usual, as I said, a caveat here that the denominator can't be zero. And finally, the limit of a sequence to a power is equal to the limit of the sequence raised to that power. So I want to look at some examples here that show how we can take the sequence limits that we saw in the previous lecture and combine them with these properties to get the limits of some new sequences. So this one here, I'm going to start by rewriting this a little bit. I'm going to make this the limit as n approaches infinity of 1 plus 1 over n. Then I've got a limit of a sum here. So this is equal to, this is that first limit property. This is equal to the sum of the limits. The limit of a constant is just the constant. So this is 1. And the limit of 1 over n is 0. So the limit of this particular sequence is going to be 1. So here I've got some constants floating around in my limit. I've got the negative and the 2. So if I use, I think it was the second property, the one that says I can pull a constant out, this is the same as negative 2 times the limit, n goes to infinity, of 1 over n. Of course, that limit is 0. So this is negative 2 times 0, or 0. So I got one more here, 1 over n squared. There's a couple of different ways we can look at this one. One is to think about that exponent, right? 1 over n squared is the same as 1 over n squared. So if we take the limit here and do the limit here, we can move the limit inside the exponent. I think this was the last rule. This is the limit as n goes to infinity of 1 over n squared, which is 0 squared or 0. Another way we could have approached this, we could have said this is the limit as n goes to infinity of 1 over n times 1 over n. Right? Then we can use the limit of a product. Say this is the limit n goes to infinity of 1 over n times the limit as n goes to infinity of 1 over n. Of course, that's 0 times 0, which is also 0. So good, we get the same result no matter which rule we use. So throughout this lecture, and the two previous ones, we've seen some similarities between the limits of functions and the limits of sequences. In the next lecture, we're going to look at several theorems that make this more precise, and then we'll look at some examples of how those connections let us calculate some specific sequential limits.